Hi! Tonight's another paper review. It is a much more toned down one than the previous ones that we've done. It's much less intense, and I think it'll also be easier to understand, but there are still a few things that we should go over before we actually start reading it. So, every decade in the field of astronomy, there is what is called the Decadal Survey. The Decadal Survey is a way to identify funding priorities for the field of astronomy, specifically in the United States. So that you can understand what the Decadal Survey is a little bit better, we're going to go over this. So this was when the 2021 was released, which was actually released in like 2021, I think, because of the pandemic. So this says, a new Decadal Survey from the National Academies of Sciences, Engineering, and Medicine identifies scientific priorities, opportunities, and funding recommendations for the next 10 years of astronomy and astrophysics. Pathways to Discovery in Astronomy and Astrophysics for the 2020s drew from the astronomical community through hundreds of white papers, town hall meetings, and the advice of 13 sub-panels over several years to produce its recommendations. The study, undertaken by the Decadal Survey of Astronomy and Astrophysics, ASTRO 2020 Steering Committee, was sponsored by NASA, the NSF, the U.S. Department of Energy, and the U.S. Air Force. The report presents a visionary plan for the field to pursue discovery and exploration of habitable planets, enhance understanding of the dynamic and changing universe, and study what drives the formation of galaxies. It recommends blah, 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 blah. It emphasizes blah, 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 blah. The rest of this is about specifically what the Decadal Survey identified as priorities. Then you can access the Decadal Survey here. We will access it later. You can actually buy a physical copy or the ebook of the Decadal Survey. So what we are reading is one of the quote-unquote white papers that was submitted to the Decadal Survey. So it's not a request for a grant, but nonetheless, what we are reading tonight is effectively a plea for funding. It's written by these three people, Samuel M. Howell, William C. Stone, and Kate Kraft, and endorsed by more than 180 other people in the field of astronomy and related to it. This is Ocean Worlds, Exploration, and the Search for Life, a white paper reflecting the views of NASA's Network for Ocean Worlds, submitted to the Decadal Survey in Planetary Science and Astrobiology. This is talking about the Astronomy Decadal Survey, right? Let me double check. Oop! Perhaps there may be an oversight. Oh my god, there's a Decadal Survey specific to planetary science and astrobiology. Origins, Worlds, and Life, 2023, the next decade of planetary science and astrobiology. This booklet highlights key science questions, identifies priority missions, and presents a research strategy that includes both planetary defense and human exploration. It's still going to be a every 10 years thing that is still identifying priorities for what should be funded, but today I learned that there is one that is specific to planetary science and astrobiology. Now that we know that, yes, so Ocean Worlds, Exploration, and the Search for Life submitted to the Decadal Survey in Planetary Science and Astrobiology, which is put together every decade to identify funding priorities for the next decade in the field of planetary science and astrobiology. Decadal surveys, the big one is the Decadal Survey in the entire field of astronomy, but they're super important because they get input from hundreds of astronomers and other people in the field about what they think our priorities should be, and then get that input to the very few people who are in charge of directing funding. So it's really important for those people to have that input of what should be funded. Oh yeah, there's one other thing we gotta go over before we start, actually. So the main thing that I learned from this paper, I did learn quite a bit more about types of NASA missions in this paper. So let's go over the types of NASA missions. There are flagship NASA missions, which is stuff like the Voyagers, I believe, and like JWST, and like, wasn't Galileo one of them? Probably. Cassini was one of them. The Europa Clipper is a flagship mission. Flagship missions are NASA's largest and most funded missions. They're huge, very exciting, very ambitious. Aside from flagship missions, there are also Discovery, New Frontiers, and Solar System Exploration missions. Discovery missions. The goal of NASA's Discovery program is to provide frequent flight opportunities for high-quality, high-value, focused planetary science investigations that can be accomplished under a not-to-exceed cost cap. By conducting a series of planetary science investigations, NASA will provide a mechanism by which pressing questions in planetary science may be addressed, permitting a steady improvement in our understanding of planetary systems and the processes that affect them. The frequent, steady nature of the investigations will ensure a continuing stream of fresh scientific data to the planetary science community, thus helping to maintain the excellence of the U.S. planetary science program and to inspire the next generation of investigators. New Frontiers. The New Frontiers investigation proposals are solicited via the Announcement of Opportunity, AO process. Each mission proposal is led by a principal investigator, PI, who is typically affiliated with a university or research institution. The PI selects team members from industry, small businesses, government laboratories, and universities to develop the scientific objectives and instrument payloads. The New Frontiers program seeks to contain total mission cost and development time and improve performance using validated new technologies, efficient management and control of design, development, and operations cost, while maintaining a strong commitment to flight safety. NASA is committed to the principles of open competition and merit review as a key to excellence. And solar system exploration missions. Solar system exploration missions vary in scope, from small, focused investigations to large, strategic missions of national importance. These include our flagship missions to answer the most compelling and challenging questions about our solar system. Because of their complexity, NASA usually assigns these missions directly to a NASA center or other implementing organization. Okay, so we gotta know about these three. All three of them will be mentioned several times throughout this paper. Now, we can actually get into the paper. We recommend the establishment of a dedicated ocean worlds exploration program within NASA to provide sustained funding support for the science, engineering, research, development, and mission planning needed to implement a multi-decadal, multi-mission program to explore ocean worlds for life and understand the conditions for habitability. The two new critical flagship missions within this program would, 1, land on Europa or Enceladus in the decade 2023 to 2032 to investigate geophysical and geochemical environments while searching for biosignatures, and 2, to directly search for life in the decade 2033 to 2042. The technological solutions for a landed mission are already in hand, evidenced by the successful Delta mission concept review of the Europa lander pre-flight project in the fall of 2018. Later in this paper, we will go over specifically what that means. Following an initial landed mission, an ocean access mission will require substantial research, development, and analog testing this decade to enable the initiation of a pre-flight project at the start of the following decade. This ambitious goal could not have been put forward with comparable requisite credibility in any preceding decade. Both science and technology have now matured so that we may prioritize the direct search for signs of life, applying lessons learned from planetary and Earth exploration to in situ investigations of worlds where water and life are most likely to exist today. In situ just means on-site, as opposed to remotely. This new era of planetary investigation will require significant support for cross-disciplinary research and development, bringing together planetary scientists and engineers with those that study the Earth. To chart these new waters, get it? A diversity of disciplines must be accompanied by a diversity of experience, skill, and perspective. All facets of this Ocean Worlds exploration program must actively ensure equitable access and inclusion across the spectrum of contributors in planetary science, exploration, and astrobiology. Hence, we recommend an Ocean Worlds exploration program that includes specific initiatives designed to entrain and retain scientists and technologists from historically underrepresented groups and to support a healthy work-life balance that enables equitable participation from across the entire community. An Ocean Worlds exploration program will provide opportunities for advancing exciting technologies to climb the ladder for life detection, a framework to further the search for life that begins with a foundation in habitability. This program will spur a new era of innovation within NASA as it pursues one of the most fundamental science quests of the Science Mission Directorate and humanity as a whole, the search for life elsewhere. We champion the value of Ocean Worlds exploration as core to NASA's science strategy and as the best path to, quote, challenge assumptions about what is technically feasible and enable revolutionary scientific discovery through a deliberate focus on innovation, experimentation, and cross-disciplinary research. I know the authors wrote this part and they were like, oh, we cooked with this, because they pulled a quote from what is probably the Science Mission Directorate. NASA's Science Mission Directorate is just this statement that NASA releases, I don't remember how frequently, that's just saying like that they commit basically to keep doing the things that they're doing. All of the things that they're doing. Their outreach, their education efforts, their research, their funding of research, their exploration of the solar system, all of it. Okay, that is the summary. Before we move on, let me also clarify, the word habitability is thrown around a lot in astrobiology. Naturally, you would expect it to be. However, it is important to clarify that there is a difference between a location being habitable, that being able to support life, and a location being able to support the development of life. A location being able to support the development of life requires more than just being able to support existing life. So habitability means whether or not a world can support life that has already developed into life. And there isn't really a single word to express the criteria for whether or not a world can support the development of life from unliving material. So oftentimes the word habitability is used to just mean both. Okay, let's move on. Given that the Ryugu samples managed to get contaminated already, is it really a good idea to send landers yet? The Ryugu samples are on Earth. That is very different. Also, if you don't do something because you think, oh no, what if something goes slightly wrong? You should not be in scientific research. Science drivers. As a NASA Astrobiology Program Research Coordination Network, or RCN, the Network for Ocean Worlds, or NOW, was established to advance comparative studies to characterize Earth and other ocean worlds across their interiors, oceans, and cryospheres, to investigate their habitability, to search for biosignatures, and to understand life in relevant ocean world analogs and beyond. Real quickly, it's not super important what an RCN is, but it is a little bit confusing. What is an RCN? A Research Coordination Network, RCN, is a virtual collaboration structure that helps support groups of investigators to communicate and coordinate their research across disciplinary, organizational, divisional, and geographic boundaries. NASA has modified a mechanism utilized by the NSF, that is National Science Foundation, to achieve the research goals for the astrobiology program. They are a mechanism for community collaboration. And I think RCNs are actually astrobiology specific, though there may very well be similar programs in other departments of NASA. The recognition that life can be chemically sustained and possibly first emerged in the darkest reaches of Earth's deep ocean made the discovery of a deep global saltwater ocean beneath Europa's icy shell a watershed moment in planetary science and astrobiology. 2 decades later, the ocean worlds of the outer solar system now present the best opportunity to find life in several possible states. And the states listed here are really interesting. You know, it's most exciting if we find life right now, like things that are living and functioning as living forms, and metabolizing and reproducing and all of the things that life does. But this mentions the possibility of finding life in several possible states. Metabolically alive and active, alive but dormant, or lifelike in form but no longer living. There is also the possibility that ocean worlds possess prebiotic environments where life has not yet emerged, providing a pristine look into early crucibles for life. That is, if we swim around in the subsurface oceans of Europa or Enceladus and we do not find life after a very extensive search, then we can start asking why. What ingredients do they have for life? What ingredients do they not have for life? And what are they missing as such? Or it would be especially interesting if we thought they had everything and then they still didn't have life. Did they need more time, etc.? Is there something we're not factoring in? I stand by, even if we somehow manage to prove definitively that there is not life in Europa's subsurface ocean, which is hard to do. It's a lot easier to prove something exists than to prove something doesn't exist. But hypothetically, if we did, I still think it's very much worth researching. Even astrobiology aside, Europa is a very geologically interesting location. The excitement associated with ocean worlds is attracting a diverse new cohort of scientists who have not traditionally been involved in solar system exploration. Wait, I think I forgot to go over something. Cryosphere, to clarify, a cryosphere is just the icy or frozen parts of a body. Experts in Earth's oceanography, glaciology, polar environments, and extreme environment microbiology. Planetary scientists from established disciplines such as geophysics, geochemistry, orbital dynamics, and astronomy are now working closely with terrestrial scientists to meaningfully advance theoretical modeling, comparative planetology, laboratory experiments, and analog field studies. Detecting life on ocean worlds is also synergistic with the Network for Life Detection, RCN, so there's another relevant RCN, and studies of ocean worlds offer a compelling opportunity to challenge our understanding of the habitable regions of our solar system, including Earth and exoplanetary systems, relevant to the goals of the Nexus for Exoplanet System Science, RCN, another relevant RCN. The oceans of Europa, Enceladus, and Titan have emerged as key targets in the search for extant life, as opposed to past life in the solar system. If you want past life, I think we mostly look at Mars for it, maybe Ceres. The icy shell of Titan is likely too thick and hazardous for near-term robotic exploration of the ocean, where habitable environments are most likely. But the icy outer shells of Europa and Enceladus, which may be a few kilometers to a few tens of kilometers thick, provide surmountable new environments to explore. Europa and Enceladus possess global oceans in direct contact with rocky interiors, providing the potential for water-rock reactions. Remember, we heard about these in one of the previous two papers. I don't remember which. Just, it's literally what it sounds like. Interactions between water and rock. Potential for water-rock reactions and a range of environments in which life could emerge and persist. Importantly, they also exhibit ongoing geologic activity, driven in part by gravitational interactions with their respective host planets, permitting surface interior material transport that can maintain chemical disequilibria in the ocean and at its interfaces. Thus, the key components for life are present: water, chemical building blocks in disequilibrium, energy, and time. Okay, there's actually quite a bit to unpack in these last, 2 sentences or so. So surface interior material transport is what we talked about in the September paper, where material from Europa's surface is moved towards its ocean and material from Europa's subsurface is pushed up towards its surface in this sort of solid state convection that we don't fully know the details of how it works. As such, since there's this cycle of materials, there can be a replenishing and diminishing of chemical species that exist in Europa's subsurface ocean. And I believe that's what this means when it says chemical disequilibrium. Usually, the disequilibrium isn't mentioned immediately when we talk about what life needs. However, life does need a consistent supply of the elements that are needed for life. If the elements are there, but in a limited supply, then maybe life could start, but it's not going to continue. And the chemical building blocks for life, usually when we talk about those, we talk about CHNOPS, sometimes with a K at the end. Those are, I think by mass, by percentage of mass, the most abundant elements in life as we know it. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and sometimes we also include a 7th, potassium. Also, as for time, life needs time, but I don't know how well we've narrowed down how much time life needs to develop. However, Europa is of similar age to Earth, actually. Fun fact. So recall, NOW is the Network for Ocean Worlds, RCN, and this table has priority themes and questions in planetary science and astrobiology according to NOW. So, under life and habitability questions, I gotta turn my head sideways. Has life emerged within ocean worlds, and does it persist today? What are the habitable environments and interfaces of ocean worlds? How do ocean worlds inform our assessments of the habitability of exoplanet systems? Planetary formation. How did ocean worlds form, and how did they accrete their volatiles? What is a volatile? Volatiles are elements and compounds that can be readily vaporized. Frankly, I don't see how, by that definition, they're astrobiology relevant, because my chemistry knowledge is fairly lacking. However, volatiles include water, methane, oxygen, carbon dioxide, and more. And those are very relevant to life. Water because water, carbon because it is the most abundant element in life as we know it, and it's in carbon dioxide, oxygen because it's one of those most abundant elements in life as we know it, etc. How are organics delivered to and synthesized on ocean worlds, and how do they evolve? What can the chemical building blocks of ocean worlds tell us about the evolution and transport history of these materials across the solar system? Planetary evolution. What are the key interfaces that permit and regulate thermal, physical, and chemical exchange? How did differentiation occur for the key geologic layers, the ice shell, ocean, and rocky interior? What tidal interactions and other sources of energy power change within these layers? And comparative oceanography. Comparative oceanography, it's kind of self-explanatory. It is a field of comparing oceans. And then in this paper and in the field of astrobiology, it means comparing oceans that may not all just be on Earth. What analog geological processes on Earth might provide insight into the sources of chemical energy that may render an ocean world habitable? How do the diversity of chemical reactions that arise on ocean worlds fuel potential life-supporting metabolisms, and how do they vary in time and space? And how and on what timescales are biosignatures transported, modified, and preserved? Hey, this question? We read a whole fucking paper all about that. That was the July paper. You guys remember that, right? Continuing. Embodied in the search for life is a focus on the planetary and local conditions that enable or restrict the emergence and persistence of life. This includes exploring the range of habitable environments present in the outer solar system and expanding the techniques for accessing potential habitats and identifying signs of past or present life. Hence, the search for life among ocean worlds can fulfill a major role in both planetary science and astrobiology, if it simultaneously addresses key questions related to planetary system and body processes, focusing on the physical and chemical processes that shape these environments. Questions like the ones that we just went over. Okay, realistically, if you ask a researcher, hey, what are you going to find with this research? There is, hypothetically, if we had infinite funding, there is value in almost all research. You can usually expect to find something. But it's a lot easier to get money and a lot easier to convince people that your science is important if you have a list of questions that you actually intend to answer. Priority missions for the decade 2023 to 2032. Here we outline a systematic pathway to ocean access and life detection by 2042 that will build upon current flight projects to explore ocean worlds. See Figure 1. We will look at Figure 1. These include the flagship Europa Clipper flyby mission to investigate the habitability of Europa, and the New Frontiers Dragonfly mission to traverse the surface of Titan, a first in the outer solar system. Recall, Europa Clipper launched in October. It's on its way there, it's doing well. It's even deployed a few of its instruments. And the Dragonfly mission is basically a drone that's meant to fly around, actually not all of Titan. I think a small section of Titan, which is a moon of Saturn. A moon of Saturn with a very thick atmosphere. We've landed on Titan before, actually. We have never been to Europa before. We've never had a dedicated mission that's specifically to observe Europa. But Titan, we've already landed on. Cassini, which was a flagship scale mission that went to Saturn, and it's in one of the diagrams later in this paper that doesn't actually say when it launched, but it ended within this past decade. Cassini had this little guy on it called the Huygens probe that detached from Cassini, entered Titan's atmosphere, landed on it, took some pictures, got us some data, found out that Titan is very, very orange, and it landed on kind of a squishy, marshy sort of surface, and then died after 45 minutes. I don't remember what caused it to die. That's your review on what the Europa Clipper is and what Dragonfly is and will be. Contemporaneously, all right, I gotta be honest, brother, get your head out of your ass. Academics, including myself, are such fucking snobs. Contemporaneously, you know what that means? It means at the same time. Contemporaneously. ESA's L-class JUICE mission, L-class just means large, will be the first designed to assess the relative habitability of multiple ocean worlds within a single planetary system. Timely completion and launch of Europa Clipper and Dragonfly and sustained international partnership in relation to the JUICE mission are central to advancing planetary science and astrobiology in the next decade. Okay, the most critical new mission in the coming decade required to progress toward life detection is a landed mission to either Europa or Enceladus. The choice between first visiting Europa or Enceladus for surface and interior exploration should be made according to knowledge of each target at the time of selection, including habitability and potential for extant life, and technology and mission readiness. The Europa Lander Science Definition Team Report and Enceladus Orbilander Flagship Planetary Mission Concept Study, among others, Provide strong science rationales for biosignature detection and environmental investigation of each planetary surface. I did not deeply look into what these two projects were, because this sentence tells you everything that you need to know about them for this paper. Provide strong science rationales for why we should visit and what we could do with Europa and Enceladus. Chemistry resulting from life may be retained in the non-ice materials of an ocean world's icy shell, e.g. organic structurally modified by life, byproducts of metabolism, providing compelling evidence for the existence of life, even in the absence of life form detection. Detecting these biosignatures is a priority science objective for any in situ ocean worlds mission. Chemistry resulting from life being retained in materials, as we learned in the July paper, it could also be retained in ice on Europa on pretty large timescales at depths that are not crazy absurdly deep. Europa is subject to more intense radiation than Enceladus is, so I would assume that if there were biosignatures in Enceladus ice, they would be even more accessible than any in Europa's ice. In addition to the search for biosignatures on an ocean world, a landed mission is crucial for investigating geophysical and geologic context and ground truthing remote sensing data. Ground truthing just means using in situ data to verify. Well-defined measurements will provide a strong foundation for inferences regarding the balance of physical and chemical processes in the ice and ocean, as well as their influences on habitability. Even in the case of a non-biosignature detection, surface measurements will continue to be valuable for considering the influence of landing site selection, radiation processing, and geologic and geochemical context on biosignature prevalence and degradation. A landed mission on Enceladus or Europa will also be enabling for future ocean access and direct life detection in a planetary ocean, where the most habitable interfaces are likely located. Characterizing the environments on the surfaces of and within ocean world ice shells will provide key engineering and design constraints for ice and ocean access technologies under development for deployment in the 2030s and retire the risks associated with landing and deploying such payloads. This is what I said we would go over more later about. In 2018, the Europa Lander pre-flight project passed its Delta Mission Concept Review, proving pre-Phase A readiness to land on an icy airless body with unknown lander-scale surface topography in the outer system. So, Phase A in mission development with NASA means the preliminary analysis phase. That means you are not building anything. I don't think you're even making blueprints or deciding what instruments. It is assessing what you plan to do, the location that you plan to go. And this is pre-Phase A, so not even that far, but ready for that. If you just Google Europa Lander Mission Concept Review, you will find far more recent things than 2018 that say, hey, we have the technology to land on Europa. We should push a mission for this to Phase A now. Unknown lander scale surface topography. What that means is that the best understanding that we have of Europa's surface is very large scale. It is not refined to the precision of the scale that a lander needs to know where is a good landing spot. And the one-way light time, that is the time it takes a signal from Earth to get to Europa, for Europa, is close to an hour. So we would be sending a lander and not knowing where it was going to land, other than somewhere on Europa. Maybe a little bit more specific than that, but this lander would have to be able to choose its own landing site. And this is saying that reviews have shown that that technology exists. We therefore advocate that a landed flagship mission capable of performing in situ biosignature detection and ascertaining the geophysical and geochemical conditions on Europa or Enceladus advance to Phase A as rapidly as possible. Yeah, it should! Biosignature detection, recall we talked a ton about that in the July paper. It would not have, depending on where it landed, it would not have to dig very deep at all. I think even in the most irradiated parts of Europa, maybe 10 centimeters deep for biosignatures. After a landed flagship mission, the next highest priority ocean worlds missions for the new decade are an Enceladus or Europa Plume fly-through mission and or a Titan Global Surveyor mission. Recent proposals have already demonstrated that these concepts can be accomplished under the New Frontiers cost cap. Remember when we went over that? Cost cap, New Frontiers. We went over that, right? Before we went over the paper. Therefore, we strongly recommend that ocean worlds, including Titan, be retained as permitted targets under the New Frontiers program. Plume fly-through. The so far unparalleled cryovolcanic activity at the south pole of Enceladus and growing case for water vapor plumes at Europa offer windows into the habitability, chemistry, and geological processes within these bodies. So, cryovolcanic volcanoes, but make them ice and maybe water. I think it was one of the Voyager probes that first detected plumes on Enceladus. Enceladus has a lot of plume activity at its south pole. So much, in fact, of these frequent geysers of ice that one of Saturn's rings is caused entirely just by ejecta from Enceladus. Europa water vapor plumes, those are iffy. There was some detection that we suspect was caused by plumes by the Hubble Space Telescope in like 2014. And then I'm not sure that JWST has found data that supports that. I think this paper was published before the most recent thing that I have come across that talks about plumes on Europa and whether or not they're likely. Sampling material from these plumes and characterizing any corresponding mechanical or geodetic. Geodetic means related to the shape and area of the land. Geodetic changes in the ice shell will allow high-fidelity investigations of interior volatile reservoirs and their habitability, illuminate geologic environments and processes, and potentially allow for biosignature detection. Titan Global Surveyor. Titan is key to understanding how distributed organic materials and an active methane cycle react with water to potentially create chemical nutrients and building blocks for life. The selected New Frontiers Dragonfly mission will make critical point measurements at several locations near an impact crater and dune fields on Titan. Yeah, so this says, like I said earlier, Dragonfly, despite being a drone, I don't think is actually going to fly like all the fuck around Titan. I think it's going to stay in a contained area near an impact crater and dune fields. Observations by a future orbiter or atmospheric mission would place the Dragonfly point measurements in a larger context with respect to Titan's geologically diverse terrains and provide insights to the coevolution of the atmosphere and surface. This will illuminate the coupling between the surface organics and the vast subsurface ocean, a potentially organic-rich habitable environment. This is actually a good opportunity to go on that Titan tangent. Just real quick, though. Dragonfly is in the active development phase, I'm pretty sure. Dragonfly has been on the table knowing that we have secure funding for it. Like, it is going to be built and happen for a while now. So Titan is a moon of Saturn. It is the second largest moon in our solar system. It has a very thick atmosphere, and on Titan's surface, there exist methane lakes, oceans, I think even rivers. Titan has its own weather cycle that uses methane instead of water. Methane exists on Titan in all three forms, solid, liquid, and gas. It's got this whole fucking like Earth-like system, but it's with methane because it's cold as fuck there. So geologically diverse terrains. It's got like lakes and oceans. Titan sounds like a cool moon. Titan is a very cool moon. Yeah, and one thing that I completely forgot to mention that is actually like super duper important for this paper, Titan also is suspected to have a subsurface ocean, which is crazy. Its surface and atmosphere are already cool enough, but then it's got a subsurface ocean. That's so cool. Let me get you a visual on Titan. You know how I said its atmosphere is really thick? This is what Titan looks like to the naked eye. Just a lot of methane clouds. But we have landed on Titan. Huygens landed on Titan and saw this. Globules, probably made of water ice, 10 to 15 centimeters in size, lie above darker, finer-grained substrate in a variable spatial distribution. And the first image released from Huygens, taken from an altitude of 16 kilometers, showing what are speculated to be drainage canals flowing to a possible shoreline. Like, this is shit you would see with water on Earth. It is so cool. Yeah, dude, honestly, if I had to describe Titan in one word, and that one word is like, has to be a super common word in the English dictionary, orange. I just call it orange. Okay, so figure 1, the now recommended Ocean Worlds exploration program leading to ocean access and life detection in the decade 2033 to 2042. Gray boxes depict funded or flown missions. Solid blue boxes depict new missions, and blue hashed boxes represent research, analysis, and technology maturation. So gray missions, funded, they will happen. Juno, Europa Clipper, JUICE, all three of those have already launched. Juno is already at Jupiter. Juno's been at Jupiter since like, oh gosh, 2015, maybe give or take like 2 years. I don't remember exactly. Dragonfly has not yet launched, but we know it's happening. I don't know what its current status is. And if you see on the left here, these are, so up above, they're classified by decade, 2013 through 2022, 2023 through 2032, and then next decade, 2033 through 2042. They are suggesting a flagship mission for ocean access and life detection. Prior to that, a blue, what do they call it, hashed box, indicating the necessary development and research into the technology that would require. And on the left here, see it specifies flagship missions, New Frontiers missions, and Discovery missions. So in terms of the scale of these missions. And which of these categories that mission falls into also relates to, does the mission have a cost cap? And what is it? This paper is 8 pages, although the last page is... No, it's like actually fully 8 pages. We're on page 6 now. I said this one was going to be a lot less intense than the last 2. You see what I mean? While the priority for an ocean worlds exploration program should be to pursue in situ studies on confirmed ocean worlds to advance the search for life, the program should also seek to verify and explore potential ocean worlds elsewhere in the solar system. Foremost is Neptune's moon Triton. Triton is quite interesting. God, I wish we knew more about it. So do these people. Which exhibits a geologically young surface, dynamic geologic environment, and potential for sustained interior activity. Neptune's moon Triton. We have never had a dedicated mission to Neptune or Uranus. Both of these planets are so underappreciated, and God, they need dedicated missions. However, Triton is a moon that we suspect may have a subsurface ocean. How long would it take to get to Triton if we did launch a mission to it? Yeah, that's the thing. Oh my God. I don't actually know off the top of my head. If I had to guess, maybe 15 years. Oh, actually, it took Voyager 2 12 years to get to Neptune. To be fair, Voyager 2 had very great circumstances. Okay, where were we? The moons of the ice giant systems, which may harbor oceans, could be investigated within the cost cap of a Discovery-class mission, as demonstrated by the proposed Trident mission, or as part of a larger ice giant system mission in the New Frontiers mission class, or as a flagship. That's ambitious, but you know what? If you want to give us a flagship mission to check out Triton, fucking do it. In the case of a broader ice giant system mission, the primary science objectives should include a significant focus on ocean detection and characterization for comparison to previously discovered oceans, Europa, Enceladus, Titan, Ganymede, Callisto, in order to advance our understanding of physical and chemical processes that control the relative habitability among the diverse set of ocean worlds. This paper might also be before that one singular paper came out that said, hey, Mimas might have a subsurface ocean. Despite the scientific potential of ocean worlds, programmatic constraints are insulating the exploration of these targets from innovations in spacecraft technologies. Low-cost, tailored investigations that address questions cited in Table 1 would increase the cadence of ocean world science return, allowing future investigations to respond to new discoveries. We therefore recommend that considerations be made to permit the exploration of outer solar system targets in lower cost cap, small satellite, or small sat mission classes. A small satellite, it's literally just what the name says. We recommend removing Phase E costs from the cost caps associated with these programs to make cost comparisons more agnostic to mission cruise requirements. So Phase E in a NASA mission is post-launch. So the budget for Phase E means covering like staff wages for those that are on the ground communicating with the mission, reducing data, etc. Which naturally Phase E is going to last longer if your mission takes longer to get to where it's going, which any mission that this paper is suggesting would. That's why they recommend removing Phase E cost caps. Specifically, the long duration of outer solar system missions requires long interplanetary transits, increasing the programmatic costs. Additionally, we recommend that NASA establish an aggressive life testing program for small sat technologies to extend reliability to outer solar system mission durations, as well as a program for small-sat planetary protection considerations. These analyses are cost-prohibitive on a case-by-case basis. Small sats may be carried to their destination by a primary host spacecraft to improve science return. Reserving resources within larger mission calls for opportunistic small-sat ride-alongs may greatly increase the accessibility of ocean worlds. So what they're suggesting here sounds like it's basically the same thing that Huygens did on Cassini, just like hitching a ride. Okay, there's a few terms coming up that I underlined as like I should define these and then proceeded to not actually look them up before stream, so we'll have to do that when we get to them. Research, analysis, and technology development. We recommend that NASA establishes a sustained research and development program in the coming decade, 2023 to 2032, for scientific research, deep surface ice and ocean exploration technologies, and instrumentation, within a broader ocean worlds exploration program to enable ocean access and life detection in the following decade of 2032 to 2042. Research and analysis. At the core of ocean worlds exploration in the coming decades should be a well-funded, oh, I wish, that's really cute, and sustained research and analysis, or RNA program. Priorities should include continued support for analyses of past, current, and future mission data, while encouraging new and novel studies into ocean world processes, including the emergence, persistence, and biogeochemical ramifications of life. This approach will broaden our understanding of the key measurements needed to confirm life beyond Earth, supporting theoretical, laboratory, modeling, and terrestrial investigations into comparative oceanography, ice physics, and multidisciplinary cryosphere research will build an empowered community capable of answering key questions to guide future exploration. They basically say it, but let me emphasize, one thing that the authors of this paper emphasize a lot is how interdisciplinary all of this is. Astronomy in itself is already a very interdisciplinary field. Fun fact, while there are very few job opportunities in the field of astronomy, astronomers are highly employable people because astronomy is such an interdisciplinary field. Astronomers, in addition to knowing all of our fun astronomy things, we know a fair amount of chemistry, we may know a fair amount of geology if we do planetary science, we know how to work with numbers, we know how to program, we know how to work with instrumentation, we know optics, we know physics, needless to say. Astrobiology and planetary science are also extremely interdisciplinary. Like, their names in and of themselves do not exclude them, do not restrict them to just one singular field. I know chemistry. Personally, my chemistry knowledge is not very good. We are fortunate to live on and explore an ocean world. This is a hilarious sentence because if Earth didn't have oceans, life very well could have never developed here. But you know what? Sure, fortunate. Strong synergies between icy moon exploration and the studies of polar oceans and ices on Earth can expand our capabilities for interrogating these environments throughout the solar system. An ocean worlds exploration program geared for success in the search for life must devote significant efforts to developing exploration technologies and instruments and associated detection limits, which will include a strong analog test component. We recommend that analog research and field testing of exploration technologies and instrumentation continue under expanded and sustained funding. As we understand the increasing likelihood that ocean worlds are common in other solar systems, accounting for potentially 1 in 4 volcanically active exoplanets, fostering collaborations with exoplanet researchers may yield new and challenging ideas about the habitability of other worlds. In addition to studying extrasolar systems, ground-based and space-based telescopes can augment ocean worlds missions in order to study time series phenomena, provide global context, and investigate the properties of yet unexplored surfaces. Exploration Technology Development. In 2017, NASA commissioned a Keck Institute for Space Studies, KISS, investigation into subsurface access on ocean worlds. This study surveyed more than half a century of research into deep ice access technologies in the context of our current understanding of the icy environments of the outer solar system. One technology concept emerged to be robust against the potential hazards and challenges of planetary exploration: the ice penetrating robot, or cryobot, that can effectively penetrate ice shells tens of kilometers thick, starting initially in a vacuum at cryogenic temperatures and descending under control through the ice column, into and through an ocean water column. Remember when we did watch a few videos of what a landing on Europa might look like? They showed this. A cryobot drilling through Europa's ice, reaching its ocean, and then releasing a hydrobot. The 2017 KISS study concluded that for the first time, the science and technology of ocean access have reached a level of maturity to credibly enable flight implementation within the next 2 decades. NASA's Science Mission Directorate then took the next step towards ocean access by establishing the Scientific Exploration Subsurface Access Mechanism for Europa, or SESAME program. Cryobot technologies to enable planetary ocean access missions are now in the engineering and development phase. Ocean access technologies require robust development, integration, and analog testing this coming decade to enable flight readiness in the 2030s. Cryobot development priorities include heat and power systems, through ice and in-ocean communications, thermal management, autonomy, mobility, scientific instrumentation, and planetary protection. A lot of these priorities I feel like are fairly self-explanatory. This is one that I have wondered about a lot, is if we are in the middle of drilling through a lot of ice or are underneath ice, how are we going to communicate back with Earth? Autonomy, they need a lot of that, as I said, because the one-way light time to Europa, and the one-way light time to Enceladus is going to be even more. And then planetary protection is just going to be a matter of like not bringing contaminants to these environments. In addition, under ice and in-ocean mobility technologies, e.g. cryobot mobility or cryobot deployed payloads, are vital to amplify the probability of life detection in icy and ocean environments. Instrument development. Sustained development is needed for remote, in situ, and aqueous instrument concepts to ensure that biosignature detection and habitability characterization devices honed for laboratory and terrestrial field analyses can be adapted to use in space, in harsh planetary environments like Europa's high radiation, and with samples that are water-based rather than soil or dust-derived. We could go on a tangent about these sorts of devices. Trying to figure out what sort of instrument or device can detect life is actually really hard. Several NASA technology programs, e.g. IC2, I love these names, Cold Tech, Picasso, and Matisse, have initiated support for technology development with respect to ocean world's relevant science, but only for a few life detection instrument types thus far. There must be a concerted effort to both introduce new technologies and further the TRL of life detection instruments. TRL means technology readiness level. This includes instruments for detecting physical signs of life, in addition to chemical attributes of non-ice materials that could contain life or life-derived byproducts. Additional efforts are required to mature capabilities for sample preparation, collection, and transport, e.g. microfluidics, in order for planetary missions seeking signs of life to be successful. Microfluidics is dealing with fluid transport on like micrometer scale. They say preparation, collection, and transport, but I am 95 to 99% certain that they just mean collection and transport within the probe, cryobot, hydrobot, whatever. Sample return mission from like Europa, Enceladus, etc. is not something that anybody is really talking about right now. Whether or not it's technologically feasible, I actually don't know. But nobody's really talking about it. To this end, NASA should accelerate high-risk, high-reward investment in development of novel instruments, sampling, and sample access systems. That is wouldn't that be nice if NASA had the money to invest in high-risk, high-reward things? To be fair, I understand why this paper is so ambitious. First off, it has good reason to be because this shit is super interesting and it is a really hot topic in planetary science and astrobiology. Second off, because you know that your idea is absolutely not going to be one-to-one actually implemented into the decadal survey. If it gets put in at all, it's going to be dumbed down a lot. Thermal and electrical power systems. Is this the last page? It is. Accessible liquid water oceans beyond Earth are exclusive to the outer solar system. Therefore, ensuring the steady production of 238 plutonium for use in spacecraft power systems is critical to enabling the search for life. I am pretty sure that 238 plutonium is the same thing that's powering the Voyagers, where it just kind of constantly radiates heat, and then we use that. Yeah. Use in radioisotope thermoelectric generators, which is an RTG, which comes up later in this same paragraph. Additionally, subsurface exploration and ocean access technologies require the availability of high heat density radioisotope power systems, which may require the repackaging of TRL-9, that's Technology Readiness Level 9, RTG, radioisotope thermal generator components, or low volume, low mass fission power systems. The idea of putting basically anything nuclear into space, any sort of reactor, etc., I think international law prevents us from actually doing that. Except it seems crazy to me that the authors would even say that with international law restrictions like that, so maybe I'm misinformed and this would be fine. Although, when you think about like the cryobot and hydrobot, perhaps when we first visit these subsurface oceans, perhaps we should not be visiting them with a plutonium payload. Maybe we keep the plutonium above the ice? Maybe? I think that would be respectful and courteous. Like, we're there to look for life. Maybe don't bring plutonium down there. Okay, this is the last bit right here. Strategic partnerships. Coordinated ocean world studies at NASA will connect stakeholders across the planetary science and earth science divisions of the Science Mission Directorate, spurring interdisciplinary research. Internationally, outer solar system missions are exclusive to the mature space agencies, NASA and ESA. However, ISRO, which is India's space organization, and JAXA, which is Japan's, now have the science, technology, and mission planning readiness to execute Ocean World's missions, having implemented exciting, low-cost inner solar system missions. Both India and Japan have done interesting stuff on the moon, and then Japan has done the 2 Hayabusa missions, which were both amazing. NASA should encourage international partners to further Ocean World's exploration by sustaining funded programs for domestic scientists to collaborate, leveraging international funding and ideas that will benefit the community as a whole. Terrestrially, the NSF's Geosciences Directorate provides the main source of funded access to the Earth's cryosphere, a key zone for validation of Ocean World's exploration technologies and scientific payloads. Additionally, NOAA coordinates a multiple agency, multiple partner national program of ocean exploration and research that offers opportunities to access unexplored regions of Earth's oceans, while the International Ocean Discovery Program emphasizes deep ocean life, creating the potential for leveraged funding. Further, the National Oceanographic Partnerships Program provides an example of interagency mechanism to facilitate industry collaborations on oceanic research with signatories that include NASA, NSF, and NOAA. Signatories means, hold on, this is another word that I rolled my eyes at because I was like, oh, you got to use your big words, don't you? A party that has signed an agreement. We recommend that NASA, NSF, and NOAA coordinate a national program for ocean world studies that capitalizes on existing investments across agencies, incentivizing government and the private sector to embrace their diverse expertise in exploration, life detection, and comparative oceanography. This requires sustained, robust access to the Antarctic ice sheet and its subglacial water bodies for the purposes of testing access technologies and science payloads. And that's it. That's the whole thing. That took an hour and a half as opposed to the usual 4 hours that these papers take us. I was hoping that a simpler one would be kind of refreshing to you guys because I know that my viewers have varying levels of expertise in the fields of astronomy, astrobiology, physics, planetary sciences, etc. So I hope it wasn't disappointing to you guys. I was hoping maybe it would be kind of refreshing.